Good afternoon, everyone. Welcome to, I think it's the fifth lecture in the technical series. If you recall, those of you that saw last week's lecture, we were looking at this area here, the kind of final area in the structure and form section, and specifically we looked at two-dimensional shapes and how these can be transformed into three-dimensional volumes, both in compressive structures and with tensile structures. If you recall, we looked at cable stay and cable net structures. This week, for the last lecture in this general series on structure and form, we're going to look at slightly more complex, shall we say, three-dimensional 3D surfaces. And again, we will look at them in the context of compressive structures, and we will look at them in the context of tensile structures. I should say in both cases that no compressive structures are entirely compressive, because as you recall, we always need some tensile strength, and vice versa. So, as we said, structural elements can be recombined in any number of ways to generate structural form. Last week we looked at 2D primary shapes. This week we're going to look at 3D complex surfaces. I will put these charts up onto Blackboard so that you can download them. All of the lectures, I should remind you, are encapsulated in the book that Will and I put together called Introduction to Architectural Technology. Blimey, I've forgotten what my own book is called for a minute then. Nevertheless, here we are, structural logic, 3D complex surfaces. Now, if you were a mathematician, you would understand all surfaces, and those of you who are mathematicians know this as equations, effectively algebraic equations, or they could be translated into 3 dimensions in a Cartesian grid. And nevertheless, we understand them as fairly simple geometric shapes. And you will see here, along one side we have, as we discussed, as I mentioned earlier, we have mainly compressive shapes, and on this side we have mainly tensile shapes. Compressive shapes, you will hear these terms used: grid shell or thin shell structures. Generally speaking, shell structures are under compressive strength, and under tensile shapes you will hear expressions such as membrane or cable net structures mentioned, or sometimes fabric structures will be used. Unfortunately, these terms do vary according to the architect or the engineer, or indeed the part of the world that you're dealing with. So that's the two major classifications. On this side we have the geometry, or the curvature, should we say. And again, you can see that that's split into two sections. One is what's known as anticlastic shapes, and the other is known as synclastic shapes. And to put it simply, I suppose, anticlastic shapes tend towards looking like some kind of what you might know as a saddle, S-A-D-D-L-E. For example, the hyperbolic paraboloid. And synclastic shapes tend to verge towards a sphere, a spherical form. Okay, and those are the two primary areas that we'll look at. One thing that you'll notice is that the common geometry is here, and this geometry is common to either structural forms that are purely compressive or structural forms that are largely tensile. And these forms, you can probably see from these images, are generated by looking at two circles, in this case, that are linked together by a series of curves. Okay, these are known as catenoids, C-A-T-E-N-O-I-D-S. That's a catenoid. Now that curve, if you remember when we were looking at arches, I beg your pardon, I'm going back again. You remember when we were looking at arches that there are a series of curves that tend to work very well structurally, and these can all be derived from a cone, if you recall. And on top of that there is the hanging chain, catenary curves. So you decide what curve it is that you want, and you repeat that curve around the circle. That develops the catenoid. And when you start linking together sections throughout this little grid here, you will develop these two kinds of surfaces. This one, which tends to be known as a ruled surface for obvious reasons, it's actually a series of straight lines that make these connections. Okay, and the other one, for want of a better name, we call them a Pringle, after the crisp. Okay, now interestingly, as I said earlier, this geometry, which is here, is just a series of lines, in both cases a series of lines, is also very efficient structurally, and also they work in compression and they work in tension. And that doesn't look like a tensile structure, but trust me, it is. I think I have some more illustrations of it. That is the cycling track that was designed for the 2012 Olympics in London at the Stratford Olympic Park. Velodrome is the word they use. So down here we have a series of synclastic shapes, and again these are classifiable. These are known classifications. The diamatic dome, which is a combination of radial arms and diagonals, okay, which stiffens and strengthens the dome. The lamellar dome, which is sort of a double helix, as you can see. Air supported structures, where we're developing the same kind of shapes but simply using air. And finally tensegrity, which is an astonishing way of putting structure together, which I shall go into in some detail. And the geodesic, which sits in the middle again. Now the geodesic is an interesting structure because I think I mentioned this in the introductory lecture. Of all the, if you like, structural forms that have been developed over the many thousands of years of the millennia of our human intervention, artificial intervention in the world, the geodesic is one of the very few that was actually invented rather than kind of evolved from a previous design. So if you like, the arch and the vault evolved into a simple ribbed dome, which then evolved into a diamatic dome, which then evolved into a lamellar dome. Whereas the geodesic was an invention. It was invented by a gentleman whose name was Richard Buckminster Fuller, and I'll go into it in a little bit of detail later on. So here we are. We're starting with the synclastic surfaces: diamatic, lamellar, geodesic, air supported, and then generally thin shell structures, which can be either. Just to remind you, thin shell structures can be synclastic or can be anticlastic. When we mean thin shell, we generally mean reinforced concrete. So there's the diamatic dome. It's actually the Houston Astrodome. It's a huge sports arena built, I think, in the 1950s in Houston. At the time, it was the biggest volume, the biggest dome on the planet when it was built. We have built larger ones then. And you can probably see what's going on. We've got a series of radiating arms coming in one direction. We've got the circular sections, which, as you now know, are in tension because they're gripping, if you like, the dome together. And then we've got diagonals working together. So all of them working together develop these very large spans. You'll also see the principle that I've talked about many times now, of each of these ribs, whichever direction they're going in, is actually a truss. Well, it's been doubled, hasn't it? It's been doubled. So it's got a deep section. Can you just see? Each one is a truss of the deep section. And that aids the overall strength of the dome. Here's a more modern version of the Houston Astrodome. This is actually built with engineered timber, glue laminated timber beams, but exactly the same principle in operation. This one actually is in Israel, I believe. It's not a truss, it's just a deep section engineered glue laminated beams with the same principle in operation. It's a very elegant way of putting a dome together, I think you'll find. And here's the next one, the lamellar dome, L-A-M-E-L-L-A, and here's the Romans, showing that this is nothing new. There's nothing new in this technology. The Romans, bless them, left us these kind of cross sections of buildings so we can actually look inside and understand how they were put together. To be able to see the whole thing as one is quite illuminating, isn't it? Because on the outside it's actually a fairly simple pitched roof, lots of rubble and stone filling the gap, but the structure of the dome is a lamellar dome, as you can see. It's these curves that are working in both directions, the kind of double helix. Actually, it's many more than two helixes, isn't it? But that's the principle. Here's another beautiful version. This is also in Italy, actually. This is Nervi again, who I've mentioned before, P.L. Nervi, N-E-R-V-I. This is the Palazzetto del Sport in Rome, just outside Rome. Was built for one of the Olympic Games. Look at that astonishingly beautiful roof. And it kind of, you can see the way, okay, here's the helical ribs. They merge with a thin shell concrete surface. The whole thing is concrete. And then as it comes to ground, can you see it sort of breaks down into larger, more substantial, gradually bigger and bigger elements until it reaches the ground on these. It just lands, or springs from, is the expression we use, it springs from just these series of points along the edge. Very beautiful building. And there it is on plan. Or at least there are the ribs on plan. This is a dome. You know this building. It's in the City of London. It's 30 St Mary Axe, also known as the Gherkin, a Foster building. But it's the same principle. It is actually a lamella dome that's just been stretched, been warped and pulled, but it's the same principle in operation. It's a lamella structure. And as I think I mentioned earlier, it's a slightly different kind of a tower, because this is a tower that, instead of relying on a big central core, big huge concrete core taking most of the load to ground and stabilizing, giving static equilibrium to the structure, this one uses an exoskeleton. It's the lamella structure on the outside. This is all steel. You can just about see it here. This is all big steel sections that the floors are hanging off. They're hanging off those steel sections. This is Foster again. I guess he likes this kind of principle. This is the atrium in the middle of the British Museum. Some of you might have seen this already. I'm not sure if you have. Interesting structure. It's this used to be an open area at the British Museum, so it's a quadrangle, a rectangular quadrangle actually, with a circular library in the centre. This is the library of the British Museum, and it's a circle in the centre. It's quite an interesting story, because actually when they designed it originally, they realised that when they actually measured it, there was it was a symmetrical roof structure. So there's a series of radiating ribs, and then there are ribs that are coming off tangentially, a little bit like a bicycle wheel, like the spokes on a bicycle wheel, creating a whole series of triangles, which were all the same size. But of course, when they actually went to measure the building, they found out that the circle, their reading library, was not, unfortunately, in the center of the quadrangle. It was slightly offset. And of course, the engineers and architects then started pulling their hair out. That how are we going to calculate every single triangle now when it's just not quite in the middle? And this is actually, believe it or not, the beginning of what we now call parametric modeling. And some clever person, I think it was at Bath University, and his name I forget, but I will credit him at some future time, designed a computer program. And I saw an early prototype of this computer program. So there was a circle in the middle of a rectangle. There were all these connecting lines, and he literally grabbed the circle and pulled it slightly, and everything then optimized around it. What optimizing means, and that's what parametric modeling is minimize the number of the number of sets of triangles that you're going to need, because in the end this is a manufacturing problem and this is a cost problem. How many different sizes of triangle are there going to be? How many awfully complex little connections are there going to be? So this program optimized or minimized the number of sets of triangles. Anyway, very interesting. That's how you develop the lamella structure. I will put that online with some explanations for you. You can go into it in more detail on your own. So here's Buckminster Fuller's one of probably Buckminster Fuller's most well-known geodesic structure. It's in Montreal in Canada. Those of you that like watching Formula One will see it because the track that they use kind of snakes its way around near this structure. When it was built, it was actually each one, the outside skin, it was skinned, if you like, with polycarbonate, so it kept the inside warm and dry. Now, Bucky's idea was always that you make one big envelope to deal with one thing, which is the weather, and then you build structures inside that envelope. There's a lovely illustration somewhere of him, of a design for one of these over the whole of Manhattan. So you solve one problem with the envelope, and then you can build whatever you like inside, and you don't have to worry about keeping it warm and dry. Anyway, this was at one time covered completely in polycarbonate panels, and also one of the very early passive solar systems, because of course, if you cover a dome with polycarbonate or glass, it becomes a greenhouse, and it can get very hot inside. And Bucky knew this, so there was a series of shades, canvas I think they were, some kind of fabric shades that would deploy as the sun tracked around as the sun tracked around the geodesic. The shades would open and close to prevent too much solar gain. One of the things about the geodesic that Bucky thought was interesting was that it was made from lots of actually really quite delicate and small struts, as you can see. Now, it's not one, again, like everything, we go over this over and over again, it's not one thin layer of struts. It's a space frame. Again, it's a space frame that's been warped into the spherical shape. It's a deep section. You can possibly see it a little bit better here. I'm not sure. It's fantastic. But because they're all made of exactly the same dimension struts, they're tiny little things, almost like a spider's web, aren't they? People that have been there, that actually go to visit and go inside, say that when you're looking out into the countryside or into the sky above, this begins to disappear. Because it's so thin and delicate, it actually disappears, and you really see through it quite well and quite clearly, which you wouldn't think, I suppose, when you look at that. But anyway, apparently that's the reality. Also makes the building of it very, very simple, because all the nodes are identical. All of these are what you used to call man-handleable, very lightweight, easily lifted. You don't actually need scaffolding to build a geodesic. You can climb. I've seen pictures of people climbing up and building it as they go. So that's interesting. This is not actually the one we just looked at. It's another one of Bucky's geodesics. Nevertheless, did I say, or did I remind you, that this is the most efficient way of enclosing volume? In other words, the least material. That's the beauty of the geodesic dome. The least material to enclose the maximum amount of volume. So it's very efficient structurally. It is a combination of hexagons and pentagons. It looks here as though it's all hexagons, but it isn't. The key to it, or the brilliance, if you like, of Buckminster Fuller's design was that by combining hexagons and pentagons, you develop that spherical form. We understand geodesics now in terms of what we call the frequency of triangles. And the higher the frequency of the more it tends towards a spherical shape, the higher the frequency of the dome, of the geodesic dome. So these 2V, 3V, and so on is effectively telling you the frequency of the dome. Now, again, this enables you as an architect to start making, it's design decisions, isn't it? This might work for you, or this might, or indeed combinations of things. And I have to remind you now that all the structures that we look at can be combined in various ways. They'd never have to be pure symmetry of any one kind. It might be just a section of this solves a problem for you. To some part of the dome you need to roof something or to connect various things together, and then you need some other structural form. Here's this is what we call an air supported structure. It's actually, you can see, it's the skin of a tennis court. It's very thin, lightweight material. It's so thin and light, and there's air being pumped permanently inside it. You have to go through a little air lock to enter it. It's a lovely solution to this problem of quickly inflating, quickly developing a lightweight enclosure. It's so light that it actually wants to take off, which is hence what this steel wires are doing, are actually holding it down. They're holding it down, and they go down each one goes about 3 meters into the ground and is held by a little anchor down at the bottom there. So here again, this is the architect Heinz Isler, I-S-L-E-R, a Swiss architect working in the middle of the last century, proving that with a very thin concrete shell and the right geometry, which is the key, he can make large, beautiful spans, beautiful volumes. That's it now. That was it before they'd built but there you go. Will McLean, my colleague, did drive around Switzerland looking for Heinz Isler projects and photographing them, bless him. I think he took his family with him. I don't think they were that pleased about the next Heinz Isler they were going to visit, but there you go. Here's another one of Isler's domes, beautiful. Now these little caps are interesting too, because you can see they kind of fold out. It's like they've been folded out. They actually are, although they are architecturally interesting because they're shading, this glass area here, they're also structurally important because they're reinforcing the arch. Can you see? That's becomes a big reinforcement for each of the openings in the overall dome structure. Here's another one of his projects using the same principle. So the reason we find them interesting, as I say, is because they are what engineers call minimal structures. You're enclosing quite a large volume. You're using reinforced concrete, true, but it's a very thin shell of reinforced concrete, 4 or 5 inches in old money. And here's a model from, I think this is from Isler's studio, just demonstrating this principle of bending, making the very slight bend in the structure. So it's the same sheet here. I think it's just a sheet of plastic. It's the same sheet, isn't it? Which is failing under a tiny load here. By just giving it that bend in that direction, that's a synclastic. It becomes a synclastic synclastic form. I'm just going to show you a few more very beautiful examples of the same principle at work. These are reinforced concrete from the last century again. Looking at options again, which we always encourage you to do. You're not going to solve all the problems immediately, but you can always use your technical studies, whatever it is you're doing, to lay out different versions of the same thing, can't you? So here, going back again to what I mentioned earlier, the anticlastic surfaces, or as we say, here's the hyperbolic parabola, a ruled surface. And again, isn't it interesting that the ruled surface, the lines that create the geometry here, that allow you to map the geometry, if you like, are the same lines used here. And this is, I'm not sure, I think this could be Felix Candela, C-A-N-D-E-L-A, or is it double L? I'm not sure. The same lines are used to create the formwork here. These are just logs, aren't they, that are laid out as a ruled surface in order to cast the concrete shell on top of them. Okay, so isn't that lovely? This is a nice, connects you to a very nice website if you're interested in shell structures generally, and it is in your bibliography, so don't worry about writing it down now. I've already mentioned the catenoid and how useful it is. So here we are, thin shell compressive anticlastic structures. This is definitely Felix Candela using that same principle. Just remember that it's the geometry, the overall geometry, this anticlastic geometry, that makes it possible to develop these large and rather beautiful thin shell concrete spans. This is one of his drawings. Now, again, as I mentioned earlier, you're having to design a huge amount of formwork, aren't you? Here's the mold. Is the negative structure onto which you're pouring the concrete. Well, of course, here in this case it's not very wet concrete, is it? Otherwise it would all slide off. They have to get the mix absolutely right, and there's an awful lot of steel reinforcing cage inside there that you can't see. There's the ruled surface we mentioned earlier. Another example, pure hyperbolic parabolic geometry, and it enables you to cantilever, doesn't it? It just comes to ground at, oh, is it 2 points? The whole thing comes to ground and balances. Astonishingly beautiful. There's the what I call the Pringle. I still can't find another word for it. This is called the Saddle Dome. Sadly, I don't think it exists anymore. It's one of the few. It's in Canada. There is one, funnily enough, in South London, which it's the refectory for St Dunstan's school in Catford, if anybody's interested to go and look at it. Here's some more beautiful structures of the same ilk. And as I said, you can the same kind of principle can operate, exactly the same principle operates using fabric, or fabric structures. You will naturally develop these anticlastic shapes develop naturally by pulling on fabric. Of course, there's some pattern cutting going on, isn't there? And there's some important detailing. These edges are all reinforced when you're designing fabric structures. But can you see again? It's a cable net, isn't it? It's two cable net bridges in this case, one going one way, one going the other. The two are pulling in opposite directions and naturally creating these beautiful curves and solving the problem for you. I love this little project. It's part of a project by Michael Hopkins. It's actually another velodrome. It's a little small velodrome in South London in Herne Hill, and this was just a kind of bicycle storage area. What did they do? They took a series of containers, shipping containers, bolted them together, designed a little forecourt area, and then skinned it with these nice this nice little anticlastic shapes. Arch supported, you can do the same thing. So here's a steel arch supporting the membrane. It's worth, as I said, looking at the detailing of these because you're pulling on fabric. Now you can see quite clearly here probably that there's steel wire running through, and then it's gripped at the end, and then there's another detail here, and of course you don't want to pierce the fabric at the top, do you? So here's a lovely little stainless steel ring, two rings actually, one bolted on the inside and one bolted on the other side, locking the fabric together, and then that ring is held in tension to the top of this rather beautiful timber mast, doesn't it? Look at the way the mast itself even splays, comes delicately to ground. There's a pin joint here, there's pin joints, and I've said it to you before, but there's a lot of architecture is about the detail. It's how you design these connections that solve the problems for you. There's always a third, if you like, there's a third element. There's the mast in pure compression, there's the wire, the cable net or fabric that's being pulled, there's some big masses of concrete under the ground here, but all of that has to be connected together, doesn't it? That's actually the velodrome that Herne Hill velodrome that I mentioned earlier. That's just, again, the same principle working. How do you hold where do you hold the fabric? There. That's where the fabric's connected together. But again, it's that pure hyperbolic paraboloid that makes it work so beautifully well. There it is again. And there's the details that I was just alluding to, that make it work in the end. So those were mainly, well, these are fabric, aren't they? Pure cable nets are quite worth looking at, just because the geometry is in a way it's clearer, isn't it? Because the lines of the cable make the geometry clear, don't they? The network of cables make it measurable in a way. The same principle is in operation. This is a very bad image. That's a better image of Frei Otto's Munich Olympic Stadium. I've mentioned Otto before. He was a pioneer of these kind of structures. This is it now. Again, one of Will's holiday family tours, I believe. What you're looking at here is glass. So when you think of these kind of effectively they are tents, aren't they? Big tent structures. They are very, very rigid. There's a huge amount of tension in these cables that's being pulled. You can see, almost feel the tension in these connecting pieces here. That's in pure compression, that mask. There, it's being pulled back down to ground, being pulled back down to ground. So these little nodes here are actually holding small sheets of glass in place. It doesn't move. Don't think that they move just because they happen to be cable net structures. But the overall geometry is still the same, and this is one of the ways that Friotto explored his geometric structures and then measured them. But this was, remember, before parametric modeling and computing. So they would make physical models, a bit like Gaudi's catenary curves, but hanging nets and seeing how they develop by pulling on different parts of them, and then measuring exactly the sizes and the shapes and forms that they could develop. He also, again, these references are on your also in your bibliography. Friotto also realized that if you look to nature is very efficient with structure, always has been. And even the simple soap bubble or soap films, the way that soap films come together, are what physicists and now structural engineers call minimal surfaces. The film will find the smallest path, if you like, between 2 points. So this is actually a soap film model. So what Friotto did was, this is just wire. He would take some wire, he would take the edges, just form the edges with the wire, that's all, dip that wire into soap film and put it out again, and that's the film of the soap. It will optimize, it will naturally make hyperbolic paraboloid shapes. Very beautiful things. Of course, this is a Vectorworks add-on, so now you can take a cable net, mesh, flat grid, and start pushing and pulling it and begin to optimize shapes. Now again, just to remind you, the beauty of these is that on the one hand side you're just playing around with geometry, aren't you? But once you've achieved what you want, when you put your compression masks in and you pull and you put your mass down, you put your mass down underground, you are making a workable structural form. And the grid that the geometry has naturally formed is the wire, is the cable net. That is where your cables will land. So the geometry and the structure are working in absolute perfect harmony. This is a really beautiful example of it. This is the, as I said, the Stratford Velodrome. It's designed by Hopkins. I can't for the life of me remember who the engineers were, but anyway, it is worth visiting this building. Really beautiful building. And this is how it works. It's not a thin concrete shell. It is actually wire. And so the in this case the Pringles shape, this anticlastic shape, is developed by pulling on a huge trussed ring beam around the edge. Okay, the wire is being pulled from one direction that way and the other direction that way, and as you tension the wire in both directions, it naturally develops that overall Pringle shape. And there it is under construction, just to prove that I'm telling the truth. And here's the nodes that connect once they've kind of put everything into tension, all the the grid are connected at these points. Remember again the importance of these little nodes. Now these nodes are not only connecting the wires traveling in two directions, and again we've got this principle of doubling, not one big one but two small ones do the job, and they're lighter. These also allow what's known as the cassettes, which is the actual roof covering, to be connected on top of the wire. The wire is very rigid. There's the big ring beam around the edge. It's like a crane, isn't it? It's like you've taken an enormous crane and just warped it into the shape, and that everything is pulling on that. There's those lovely little node details that I keep banging on about. There it is inside. Now here you can see that they house these, what they call them cassettes, I think, but it's basically a prefabricated panel which keeps the water out and insulates the building, keeps it warm and dry. There it is inside. Beautiful structure. And finally, or last, but by no means least, in this overall analysis, if you like, of complicated structural surfaces comes this principle of tensegrity. And again, it was an invention. It was claimed by Buckminster Fuller, but also by one of his students, a man named Kenneth Snelson, Snelson. They both have patents on this principle. This is a Lego version, and I don't know, can you see just by looking at it how clever it is? This obviously is an element in in compression, and this is obviously an element in compression, but that doesn't touch that, and yet somehow that's held up in space. And of course that's in pure tension. That's in pure tension, just stopping it all falling over, isn't it? So it's a lovely thing. And I've got an animation of this, but I can't show it here. There's a reference to it in your bibliography, so worth having a look at. But this is Snelson's work. This is some of his work using tensegrity. Now, having said that the geodesic is the most efficient way of enclosing space, if and when tensegrity becomes developed to the point where it becomes really truly three-dimensional, in other words, three-dimensional volumetric space enclosure system, it will be the lightest way of enclosing space. Snelson was developing these as you can see, as kind of as sculptures. They both called it something like floating compression, something like that. I'm not quite sure, but the key, as you can see, is none of these elements, these compressive elements, touch. They don't touch. They're held in place by the wire. And you can explore this yourselves, and I encourage you to do it, starting with very simple. It's easy to do it with elastic because you can just sort of pull it into place, can't you? Starting with a simple node like this, gradually adding, and you will see how you can develop tensegrity structures. This was a student model from some years ago. Again, very elegant. But can you see, you know, there's a volume developed here, hasn't there? That, of course, is in pure compression, and there's a few uprights that are in pure compression. But these, which is effectively the roof, the main structure holding the roof, are just held by putting wire into tension. There's an example not far from the university. This is the aviary at London Zoo. You don't have to pay to go into London Zoo to see it. You can just travel around the outside. It was designed by Cedric Price, Frank Newby and Lord Snowdon, and these tetrahedron shapes, again, you can see they don't come to ground, do they? They're not coming to ground, they're held in place. It is a pure tensegrity structure. Here's the masts, where all the compressive load eventually comes down to ground. You can see it's called the Snowdon Aviary. This is one of the few applications that we've seen of tensegrity, or so we say civil engineering scale applications of tensegrity. The deck of this bridge is theoretically spanning through these tensegrity elements. This is in Holland, I believe. Bridge. Here's a sort of similar one. It's a sort of combination of the velodrome, what we were looking at there. So this is outer rib, isn't there? This is in Potsdamer Platz in Berlin. There's the outer rib. Here's the element in the center. It's rather fantastic, isn't it? You can just see the rib here is holding this mast here in the center. So the load from most of that roof structure is coming back down into the mast, which is not hitting the ground, but is being held in tension back to the exterior truss around the edge there. Very elegant. It's a sort of combination of that principle used in the Houston Velodrome with the tensegrity structure in the center. And this is really the last image I'm going to show, well, the last series of images. This is one of the first that we know of, use of tensegrity structure to create a volume, or in this case to create a roof canopy. It was designed by a gentleman called Jeff Morrow, who hopefully sometime in the next few years you will hear come and lecture here. His company is called Structure Mode. Very interesting company. You have a look at their website, Structure Mode. I don't need to spell that for you. So this is, as you can see, it's a 10 secretary canopy, and this is us building that very same one at your campus, Marylebone campus, a couple of years ago, because it was deployable, transportable, and that's my colleague Will McLean. These are students. So it comes in a sort of kit, pre-made. Here we are deploying it. Emphasize again the importance of these little nodes, which are repeated throughout the structure. A lot of design went into them. Very beautiful even before the skin came along. The pattern cut fabric, which is again anti-clastic shape. And there we go. So we think that could be the future. So that's the end of your kind of structure lectures for now. That was me, just in case you've forgotten who I am. And of course, if you want to ask any questions about any of the lectures or anything, please do email me. It's not my Westminster, as some of you make the mistake. It's just p.silver@westminster.ac.uk. And what I will do today also is to remind you that you do have to do a little bit of work for us this year, and that your coursework is going to be to do a little bit of research and to produce some nice drawings and produce a poster is what we really want you to do. So what we'll be doing over the next week or so is attaching your name to one of the names on that list that you can see in front of you now. These are all we'd say relatively modern engineers and architects who have made a significant contribution, important contributions to the development of structural form or construction technology. We haven't included any contemporary architects because we don't think that it's appropriate yet to include architects who have not, shall we say, completed their work. So this is, you might call this the Dead Architect Society. I don't know if you want to. When you get allocated a particular name, if there's somebody on the list that you're already, let's say, very familiar with or very passionate about, please do email me and plead your case for taking somebody else on. Otherwise, just take on what's given to you. Because of the numbers of you, there'll be 5 or 6 of you dealing with each of these innovators. So yeah, that's about it for this week. Thank you very much. Good night.